Okay.
So it's our pleasure to have Misha Kafanov to continue his series of lectures about the introduction about what is basically arithmetic topology.
Okay.
And so, yeah.
Yes. So let's see what we discussed last time. So it was linking number.
Yeah.
Right. So we have linking number. So C1, C2, and Legendre symbol. Which will consider as an element of plus minus 1. You can also look at 0 and 2. Right? And so it can lie in Z, or it can lie in Z mod n, as n equals 2. Right? And the definition is that we have a manifold M, C1, C2, and Cn. So like, there are several definitions. One of them, we take twofold cut ramified along C1.
But by the way, that was a question.
Yeah. What is the condition for the existence?
Yes, and how is it constructed?
Okay. So let me discuss both. So question is, when exists? So answer, when class of C1 equals 0 in H1 of n 0, 2. Okay, let's try to understand this. Consider the following model situation. Suppose you have a circle C, which is C1. So it's a codimension 2 thing in M3. It's one dimension. So then the transversal thing is 2 dimension. Let's do this. Suppose we can represent C as the zero locus of a section of a complex line bundle. I suppose C is the zero locus of S as a C infinity section of M L, and that's a complex line bundle. And suppose this line bundle is divisible by 2, or has a square. Say L is some other bundle. Say L is morphic to M squared. Then we can embed. Then we can define until then. So it will be embedded inside in the total space of N. Total space of N. It will be sort of, if you want, a spectral curve, sense of those point M and there's a notation here. Let's call it E. Okay, let's call it E. So ME such that E squared equals S.
Sorry, I don't see S.
Suppose S is a section.
Okay, S is the section. Okay.
So then, suppose it's like transversely cuts our manifold. Then if
okay, then you have 2 of them for each point. Okay.
Yes, we have two pre-images for each point, except for where it vanishes.
Yeah.
But we want. So
yes. Okay, that's why it.
Yes. But when C equals ZS, it means that the dual class. So we identify H1 of M. We identify H1 of MZ, identify H2 of MZ. Right? So this means that the class of C, so the class of C lies here. So simply is the first Chern class. With the definition of the Chern class, the first Chern class on the level of on a manifold is obtained by taking a generic section. Look at the zero locus. It would be something of codimension 2.
Okay.
So by point coroduality, it would be it would be a codimension 2, so codimension 2 cycles. By point coroduality, H2 is homology of codimension 2, which is H1 in our case. Right? So it means that if this class is divisible by 2, then we can do this.
Because you have the epsilon.
Yes.
Okay.
But we can always represent it as the Chern class of something, because we can construct the bundle so it's outside, we trivialize it. So one can always construct L. L and S. So basically, we take a normal bundle, so M will be trivial outside. So take a tubular neighborhood, take a tubular neighborhood. U containing C. So take L trivial outside U, and here would be the standard thing given the time. And here it would be the bundle such that there will be canonical section vanishing. So it will be a trivial bundle here, and we glue them together.
Sorry, I'm not sure. How you make the trivial line bundles there. Okay.
The trivial line bundle outside the tubular neighborhood.
Yeah.
Trivial bundle in the tubular neighborhood, but then I glue them together by the identification, which sort of rotates, does a simple rotation here. So how do we construct the function? So we need a function which would we need a bundle whose natural section was sort of vanishing here.
Oh, you want the vanishing on the locus on the
yeah.
Okay.
Yeah. So and glue. So how to construct a line bundle with a section? Suppose I have a disk and C. How to construct a line bundle with a canonical section which would vanish in this disk, which would vanish at this point. So we want a line bundle for which would be like a canonical section, which would vanish at this point.
Well, there's a canonical line bundle, that's for sure. But then the question is, what is how to get the section? That's
yes, we need a section function Z, basically. Yes, f of Z equals Z, which will sort of vanish like this.
Okay.
So there is sort of canonical such function in the neighborhood of in this neighborhood. Right? There is a canonical.
Was that the distance from?
Yes. Well, the distance is not complex function.
Yeah.
It's a complex function.
Yes. Yep. Because you want codimension 2.
Yeah, codimension 2. It's not the distance, but in the complex. So which would be sort of like analytic in this direction or something, right? Well, it's sort of a rather clear procedure.
And you were saying, turning around the rotation, you were saying, because if this point in the middle is the fixed point of the rotation, right?
Yes.
So and that's why you were saying turning the.
Yes.
Yep. Okay.
So anyway, you can realize, and one can also see if there is a pre-image here. It goes to 1 to 1. So we can realize it's necessary and sufficient. But suppose that such a covering exists, then we can form the E. We can form an E here, right?
Sorry, what the E would be the line bundle?
Yes, would be E tilde would be corresponding to the pre-image
So you put back the line bundle. No.
No. Suppose we have. So let me give a different explanation. Suppose we want to consider a covering of projected line of a sphere ramified at 3 points. This is not possible with simple ramification. Double covering with a simple ramification at 3 points. It's not possible. There should be 4 points, either 2 points or 4 points.
Maybe I don't know.
The formal argument will be, suppose we go it like this, suppose this P, then we will have that P, that we will find out that P, and here we have E.
So sorry, so you suppose, I'm not sure what you want to do
Okay,
here.
okay.
You suppose that you have the covering.
Let's do it this way. So suppose the class is divisible by 2.
Okay.
Then we can form the cover.
Okay.
Okay?
Yep.
Understand? Now, conversion. Suppose I have a cover. Let me prove, for instance, that the intersection number of this C with any surface is divisible by 2. Yeah? Let me prove this. Suppose M tilde exists. So then this would be C, right? And suppose we intersect with the surface S. Yes. So clearly, surface. Intersection with T and S is 0, 1, 2.
But here, all this lives in M, or because I don't see M tiled here.
No, in M.
In M, okay.
Well, suppose we have, suppose given a surface S, I want to prove the class of the first homology is 0. For this, I will prove that the intersection with any 2-dimensional surface is 0. Well, suppose we have a 2-dimensional surface. Let's lift the surface into M tilde.
Okay.
And see what happens. It would be a 2-fold
covering, yeah.
Yes.
Outside of C.
Yes. Then S, C to S would be 2 to 1 outside C intersected with S. And then one can see that the intersection number, you can move it, so it will contribute twice at every point.
Okay. Because it's something which is stable and
yes.
Okay.
Yes.
Okay. Yep.
So that's the reason. So in order to construct the double cover, this thing needs to be homologous to 0, at least not 2. If you live in an actual sphere, it's homologous to 0 right away. There is no issue. If M is a 3-dimensional sphere, then the homology itself is 0. So there is no question. But in general, it's an abstraction to doing this. Yeah? So, and if both C1 equals to 2, then we have that C1, C2 equals, so in this case it's minus, but modulo 2 is the same, sure, minus C2, C1. Okay, now let's look at spec Z. So we want to take, it will be a sort of element of M. And C1, C2 correspond to primes P and Q. And so we want to do, naively, we want we'll take M tilde with respect Z of square root of P. So I would cover, so we would cover in a 2-to-1 way. Yeah, when it comes to this. Yes. So we do this, and then the lifting of Frobenius. Frobenius corresponding to FQ gives Legendre symbol.
I'm not sure about that part.
Oh, okay, so let's understand it differently. So here we have the C2, which is corresponds to the prime ideal Q.
Mm-hmm.
Yeah? And so what we take, so it's pi, it's P. Let's call it pi. Let's call it phi. Pi. What is pi minus 1 of C2 will be spectrum of the following ring. Spectrum FQ of x, 1 over x squared equals.
Mm-hmm.
So it is one circle, so to say. F q squared. So F corresponding will be a new finite field. So if this is irreducible, so it depends of this polynomial whether it's irreducible or not.
Yes.
Or reducible. Reducible, then it's one circle, so to say. It would be corresponding to finite field q squared. It's reducible, it is two circles. Fq plus Fq. Yes, so now when it's reducible, so reducible. So reducible means P is a square root mod Q. Is a quadratic residue mod Q.
Yes, I remember you explained that last time, I think, but I did not get where was the Frobenius actually. You said
Frobenius it's just a different way of saying that. So even for this understanding. So if in general we consider M1 M tilde over M, ramified along C1, right? So this is C1, and this is somehow is C2. We're going around C2. Right? So then if you go around C2, it will get a deck transformation of M tilde.
Yes.
So going around C2.
Okay, because before here, where you were going is the fact that actually either it's connected or not connected.
Yes, but we can say it more scientifically. We can say it in a more fancy way. Going around C2 gives a deck transformation. So in the Gauss group, so it's an element of Z1, 2. And if this deck transformation is trivial, so it's equal to 0, 1, 2.
If there's only one cover.
Then, no, if it's trivial, there's two covers. If you go around and the two fibers have not interchanged, if the deck transformation, if it's the identity.
Yeah, it means that it's disconnected.
Disconnected.
Yeah, okay, sorry. Yes.
Equal to 1, 1, 2.
Okay, so here on the right-hand side, the connectedness or disconnectedness, you would see it in the fact that it's irreducible or reducible.
Yes, and you can also say that the analog deck transformation is the lifting of the Frobenius. One can say it all algebraically, just as this.
That's the other option, yeah.
Yes, the option, but more immediately, just say pre-image is connected or disconnected. So, okay, so therefore, this thing, the analog of C1, C2 is simply equals to. We want to say that it's equal to the Legendre symbol Q. However, there is a little subtlety here. Subtlety is that the linking number is symmetric, but the Legendre symbol is not symmetric. So let's explain this situation. So there is similar contradiction, seeming contradiction. Huh? C1 is C2 symmetric, while 2 is not. Right, so let me recall, so with this we seem to have proved or to have suggested the formula that it would be equal to Q over T. It's not so. The Gauss reciprocity law indeed relates this one with this one. But there is a certain correction. It would be -1, T minus 1 over Q minus 1. This is the Gauss reciprocity. Okay, let's see why. So what really happens here? So really the issue is that when we do this, it will not be just ramified at P. It will be ramified somewhere else also. When I describe this curve of P, it may, sometimes it may or may not, and I'll explain what happens. So explanation of this, that is, so explanation. Is that if I take spec Z of square root of P, as considered as a covering of spec Z, is ramified at P always, but also can sometimes be ramified at the prime 2. Let me explain why. So what is the meaning of ramification? So let me understand ramification algebraically. So when I say ramified, I can use do it just by analogy, or I can do it more systematically. So if I have, for instance, suppose I have x and y. Suppose I have a curve f of xy equals to 0. Suppose I call this curve n. It's a curve on C2. Projects on C. Right? Something like this. Right? So the set of x is called this projection pi. Set of x, pi is ramified over x. Well, it is given by the discriminant of this equation with respect to y. Well, but so pi minus 1 of x is a set of y for which f of xy equals 0. So if you ramify, if this polynomial as a function of y has multiple roots, right? So ramify, so it has multiple roots. Has a multiple roots. Which means that we consider the discriminant in y, f of xy, is a certain polynomial called d of x. This equation. So similarly, so with respect to x, we can replace c of x. We can replace by any commutative ring. Right? So commutative ring, we call it A. Okay? And then we consider spec. We consider spec A. And then we consider here spec A of y modulo f of y equals 0. So here I don't write x because x somehow is subsumed into the ring A. Yeah? That's the same thing. So we're ramified. Well, we need to take the discriminant of this polynomial f over y over a, get an element of a, and this element of a gives the equation of this of the ramification laws. Right? D, which is discriminant y of f y, simple element. So, so in particular, if we say f of y equals y squared minus something. So suppose you want to do something, the easiest way, now take.
So the 2 is because you had the square root of p. That's why you had the 2? Or?
Yes. So take f of y equals y squared minus some element of a, minus a.
And before that, you had chosen the double cover because you were working mode 2.
Okay. So what I want to say is that the discriminant. So the discriminant of let's say ay squared plus by plus c equals b squared minus. It has coefficients. It has b squared minus 4ac. So when we work modulo 2, then it can sort of move into our face. This, because the divisors of those coefficients become important.
Yes.
So what I'm saying that if I take 0 square root of p, it will unify the 2.
So once again,
if p is congruent to 3 mod 4, then it's ramified to 2. If p congruent to 1 mod 4, ramified only at p, at 2 and np.
Because you were saying that the place where it's ramified is basically the 0 of the discriminant.
Yes.
And you are saying that discriminant here is b squared minus 4ac. So I want to understand why, if it's 3 modulo 4.
So it's actually a little subtle because it's not fully this, and we need to take there's some refinement of this. If I do it like this, it would say it will be always, so it will be always 4a. So it looks like it will be always 0, but so there should be certain refinement of this formula. Which
no, I got it. You are saying that here the b was 0, so that's why there's no b.
Yes.
Okay, makes sense. Okay.
So anyway, it's p equal to 1 mod 4. It's ramified only. So it means that it looks like the first homology of this manifold.
But I don't see where p appears here. So what?
No, this doesn't show it. So one should just explain how this 4 this formula. It's not exactly like this because we have to write what's called the ring of integers, and on this ring of integers we write the quadratic form, and it will be a two-dimensional lattice, some quadratic form there. It will be discriminant of that quadratic form. Really.
I see.
So it will be
you're saying that here there's a quadratic form hidden, but you're saying that you're changing the ring on which you're doing it. Okay.
Yes. Okay. In a proper basis.
Yes.
So in this way, it would be identically 0, which will not be the case there.
Okay.
So anyway, so this kind of affects. Let me say that this formula affects behavior logic. So the real point is that in this, if you use XZ3 manifold, then as far as homology mod 2 is concerned, so therefore, D plus P for k plus 1 has zero homology class. And if p plus 3 is non-zero and matches the class of 2.
So, sorry, in which homology?
So far I don't specify the homology, I'm just saying that existence of a ramified cover purely along the circle. So we discussed that if you have a circle and that you want to have a cover ramified only along the circle, then the circle should have zero class in homology 1, 2. If it's not zero, then I can have a covering ramified to this circle and some other circle, so that together they will be zero. So what happens here, that this, so we can say that class of p of 4k plus 3 plus the class of 2 equals 0 in homology. And class of p equals 4k plus 1 is 0 by itself. Just from the existence of ramified coverings. So there is no way, no matter what we try, we will never be able, it's not possible to have a cover, double cover, which would ramify only along those things, along this line. So not possible. So not possible. To double cover. Spec Z, ramifying only V equals 4k plus 3.
So these are kind of small black boxes, right? Here.
Yes.
Yeah. Okay. So I have to take it as a black box here.
Yes,
There's
yes.
these two cases, and by
Yes.
analogy
So
with what we've seen before.
what we do, we try,
Yeah.
and each time, so this would always appear. But if it's 4k plus 1, then it will not appear. So now this matches Gaussian reciprocity.
But even though these homology classes, they are for which homology theory?
Well, strictly speaking, we need to specify homology theory. So far, we're just thinking of naively of by analogy, so the class in homology is 0 if there is a ramified cover.
Okay, but there's one.
Yes.
What's the name of it?
No, this is called ethyl homology.
Okay, that's
more or less based
Okay.
on various ramified covers, unramified covers.
Okay. And so now you're saying that this explains the Gaussian
This explains the reciprocity law. Because what stands here? P minus 1 over 2. P minus 1 over 2 is even if P equals 4k plus 1. Or P equals 4k plus 3. So it means that it will be symmetric if, for instance, both of them are the form 4k plus 1. If both P and Q are the form 4k plus 1.
Why? Because because if you divide by 2. Okay. Yeah. Okay. Yes.
Minus 1 over 2. It's exactly the same thing which distinguishes. Right? Or if they are both of 4k plus 3, because in this case, they both come with this extra thing. And this extra thing will So anyway, this is how one can think about it. So it explains the reciprocity law, and the appearance of this is tied to simply to the fact that it's not exactly like a homologous theory. We cannot do the proper, the clean analog of linking number. We do something which looks like linking number, but it's not clean because we get a parasitic term, which we cannot get rid of.
And so here the fact that we have taken a square root of p and the fact that we are doing double cover is because we are working mode 2.
Or 2.
And so the same story will go for the mods? Or?
Well, in principle, yes. So, but the restrictions are that you have to. So there is a concept of power residue symbol for other.
Okay, it's not necessarily quadratic.
Yes, of course, yes. We can do exactly the same thing. We should just assume that we cannot work over Z anymore. should work over a number field which contains appropriate roots of units. And then it simply works like in the sketch for other modes. Other words, it's what it's called. So, it's called the power residues. So it's basically the same. We need, instead of Z, we should have the number ring should contain n roots of units.
So here instead of Z square root of P.
No, instead of Z.
But before we
and then we can take A of nth root of some. Or some element.
But in the case n equals 2, why we?
Because we already have second roots of 1. Because the
minus 1. No.
Yes, minus 1 is never a problem.
Okay.
But for Z, it would be awkward because if you take nth roots over Z, we won't get a Galois extension. We cannot even say that it's a like in the same. What will be the depth transformation? So it won't be an element of the Galois group. Because there is no Galois group. We have the Galois group in it, roots of units. And then it's absolutely the same thing. So we can be inside A, right? So or we can take like element. More systematically, we do it like this, right? A is some element in A, right? So it's an n-fold covering. So n-fold covering.
I'm sorry, I'm not sure. I said yes, but I'm not sure actually. For why do you need to have the nth root of unity to have a Galois cover?
Because so suppose it exists. Suppose let me first of all.
With the n-fold covering, okay.
The Galois. Because what is the Galois transformation? We should take a root, this nth root, to another nth root. And another nth root differs from the original one by nth root of unity.
Okay.
Yes. Yep. So if you want to have a Galois group, the only way the Galois group can act is by sending this one to another one. And for this, we need to have another one. And if we have another one, then we have nth roots of unity.
Okay.
So then we can do it a little more systematically. So RA is an element of ring, is an element of the ring, right? In a number ring, we not necessarily have a prime decomposition. We have prime ideals. And prime ideals correspond to circles, right? So there's no prime ideals. That's a Gaussian field inside A. So it will be something that the quotient A by this prime ideal will be some field FQ.
Okay. Yes.
Right? So then we can power residue symbol, which we call A. Or more strictly speaking, it's rather more canonically to the group to nth root of unity. We do like a deck transformation. It's better. So now it's better to speak about deck transformation.
So I'm not sure here. So what is? How is it defined?
Well,
that's different. That's an element of the. Okay.
It's a sort of the deck transformation corresponding to this, to the lifting of, there's a Galois group of FQ bar over FQ, and it maps into a Galois group of this extension, A.
And it's the image of the Frobenius, which is this.
Yes. The image of the Frobenius, which is also the deck transformation.
Which is this A over P.
Yes.
Okay.
Yeah. So this is the power residue symbol, which for n equals 2 reduces to so, and there is a reciprocity law. So now, so we can extend this. So in such a ring, there is unique decomposition into prime ideals. So A has unique decomposition, but not into prime elements of the ring, but to prime ideals. Any element, say B, can be written as so the ideal corresponding to element B is P1 to some number M1, PR to some number. That's the principle. So then we can define, in particular, we can define A over B equals A over P1. We just define.
So that's the definition of what's on the right?
Yes, over here.
I'm not sure, because here you
so this I defined the two arguments were not of symmetric nature. The argument of the top is an element of A, always. The argument of the bottom is a prime ideal.
So actually, I'm not sure now, because you're saying that wait. So A is just an element of A, P is a prime ideal, and this symbol should depend at the same time as on A and P. It depends on A because you're doing the extension A by the nth root of A.
Yes.
But I don't see P appear. Oh, and P appears because of FQ.
Yes. So it's called the power residue symbol. Yes. It's equal to 1 if and only if A is an nth power modulo. If the image of A in this ring, in this finite field, is an nth power, then this element is 1.
Okay. Okay, and so now.
So that's why it's called the power residue symbol. The Legendre symbol is a quadratic residue symbol equal to 1. If it's ideally, we would like to take.
And so to define that, you use the notation up there.
Yes. So
because in which sense A is the nth power? It's the ideal generated by.
No, here. So here, a priori, it is a priori. This is defined.
Well, what does it mean for A to be nth power modulo?
It is the image of A in this element. So here.
Okay. In FQ. Okay. Yes.
And it may or may not be.
Yep.
And say maybe a cube or not a cube.
Yep.
But there are different possibilities for being a cube. So the subgroup of those elements which are cubes have a large index. So by being a cube or not a cube is not kind of equipotent possibilities.
Okay.
Being a square or not a square are equipotent possibilities.
I see.
By being cube or not a cube
is not
equipotent. So being a cube is not 1/3.
Okay.
So the other 2/3 also separated into two by saying that there's a power residue symbol which take value in three elements.
Okay.
There are three ways of being power residue, cubic residue or not residue. It may be exact cube, which means that the cubic residue symbol is 1, and there is another cubic residue symbol is zeta, which is the cubic root of unity, or it may be zeta square, which would be another cubic root of unity.
And so here, what were you defining?
So now so you see the Gauss reciprocity law. There is, in order for this to be symmetric, we cannot even say because it's an element of a ring. That's prime ideal. Yeah, so let's try to have a general context in which we can invert this. So that's the classical way of thinking. Right? We can say suppose that some element of a ring. So B is an A. So normally we would say that we decompose in integers, we decompose it into prime numbers. But we cannot uniquely decompose into prime numbers. But we can uniquely decompose into prime ideals. So then we do, we write the decomposition and define the power raised to the symbol of A with respect to B. So then now A and B are elements of the same.
Okay.
The same nature.
Okay.
So now we can ask.
If this is symmetric.
So what is the relation AD and BA? So now, so it would be actually like this. So and the answer is exactly the same behavior. If so the behavior, the situation here. Situation would be like this. So if so we do A mod B. So if we do A mod B, so A mod B is related to A of square root of B, nth root of B. Right? If we B, sorry, that's square root of A. Square root of A. Yeah. A of nth root of A. Yeah. That's what we discussed.
So you mean the
symbol related to those elements, yes. So each of them is defined in terms of, so it related to the Galois group. Right?
Mm-hmm.
But now we can ask where this ramifies. Say A has prime ideals with this on Q1 to the N1, QS to the N1.
But then I'm not completely sure. So what because there the point was that there was kind of. I mean,
somehow you want to have ramification only at prime ideals of A.
Oh, you need to have the cover to talk about the Galois group.
Yes.
Yeah. So first you want to discuss the cover.
Yes.
Yes.
But then you want. So you want, but it will not quite work. So A of square root of n of A is ramified only along Q1, which are prime divisors of A. Naively, it would relate.
What you call a prime divisor of A is one of these prime ideals.
Yes, prime ideals.
Okay.
One. So and then it would be complete analogy. But it is not so bad. There will be some parasitic ramification along prime divisors of n. So, but there will be the parasitic ramification for the same reason. Like for integers, there was parasitic ramification of 2. For if you take cubic roots, there will be a ramification at some divisor of at number 3. For parasitic ramification. Divisors of n. So what will happen is this, that if both A and B are congruent to 1 mod some good power of n, then it's okay. So the correct reciprocity law right here. So in general, it's called congruent reciprocity law. In the rough form, there exists some called ideal called conduct. So basically n to some power. Right? Called ideal n. Such that, so that for A and B congruent to 1 modulo 30, we have this.
So
if
this
they are
n,
such that there is no parasitic ramification.
so n is depending on n and A and B.
So depending on A.
Yeah.
Some fixed for the ring A.
Oh, but it does not depend on small a and small b.
No.
Okay.
No. It depends only on the ring A. It's called the conductor. Yes, it depends only on A. So NA. So it depends on A and such that whenever A and B are congruent to 1 with N, then we have this problem. But in fact, that there has been further developments. You can describe this thing in general. So far it's just a statement that for a very restricted number. So in general, there's a formula which would amount to this for such A and B. So that's the first one. So in general, the formula for A and B in general. But the essence is this, that whenever there is no extra ramification, whenever we can do what we sort of naively would do for linking numbers, it works. In general, it will be not symmetric, and we can see the reason for this. The reason that it's not possible to separate, to do ramification only at those points. There will be something extra. We do the naive thing, we take nth root. What would be another way to do it? We take nth root, but there will be some extra things that will always pick up. So it's completely the same, completely simple. Okay, so this explains on some first level all the subtleties of the reciprocity law in number theory. So the reason is that some kind of homology classes of the circles are non-trivial, and therefore we cannot play the game. We cannot play the game of linking numbers. Now there are some other. One can go in two directions from here.
You mentioned the massive products.
Yes, I can mention the massive product. You can define triple linking numbers. Or yes, maybe that's it. Yes. What if I C1, C2, C3 inside a sphere? So suppose there is in a sphere, so we can discuss the lecture. And Ci, Cj, 2 equals 0. Then there exists triple linking number. Again, in 0 is a well-defined concept which has some meaning. Let me try to, again, there are several ways of defining it. Actually, even for the linking number, there is some more definitions. So definition 1. So first, I wanted to say that we should be kind of preliminary information. That if C1, C2 is 0, then there exists a covering ramified along C1 and C2, but the Galois group being the Heisenberg group, S3. Ramified along C1 and C2, and the Galois group So let me just postulate this first. Because, let me put it this way, that there is yet another definition of the linking number is through cohomological multiplication cohomology. And in this group, has cohomology exactly how should I say it? The group. So this group has H1 equals 0.2 square. H2 is 0.2. And there's a cohomological pairing here is the multiplication. It is the symplectic form. Is the pairing Z2, so equals Z2 plus Z2. Z2 plus Z2. Okay, so let me just say this first of all. But there is a covering that this type of Galois group. So first we can take a double cover. We can take cover ramified along the first one. And then we can take a cover ramified along the second one. This will give me a cover with the group 0.2 plus 0.2. But if the linking number is 0, then so this group is called, let's call it height. It's not an initiation. The highest projects here. It's a center of extension. So, and then what we can do.
So the B is the first central part, and the A and the C.
Yes, this is A and C. This is B. B is in the center.
And so, and that's...
So suppose we believe this. So now let me define an integer corresponding to C1, C2, and C3. Then let's look at the depth transformation. Along C3. This is an element of this group. In this group, in this depth transformation, both A and C would be equal to 0. Because A would be equal C1, C3. B would be equal to C2, C3. And C may be not 0. So this small c. So this is a triple linking number.
So I'm not sure where do you read that. You have C1, C2, C3 as basis where you express.
Because the projection, there's a projection here. The induced covering would be the covering of a simply ramified two-fold along C1.
So you said it, but I haven't written it. So you said that the first covering corresponds to the covering of a C1, or
so we can take a double covering ramified along C1,
yeah,
and then double covering ramified along C2.
And so the first,
and this is symmetric. It will be covering with the group Z2 plus Z2, kind of independent. It will be independent thing, right? So then A would be so image. The A part of the depth transformation would be this linking number. The C part, the C part. A. C is this, and B will be something. So that's one way of defining this.
And so this really not trivial. I mean, I'm really not sure, because the Heisenberg group, you have a collection of these with A prime, C prime. You have different values, right? So here A, C, B, they are you.
Elements of Zemo, like I said, this group.
It's over Zemo 2. Okay, so
yes.
there are not that many. Okay.
There are not too many.
Yeah.
So you have this. So that basically what we can start doing, instead of doing abelian coverings, we can start doing important coverings. This is an important group. right? So the commutator of this lies here, and this is already in the center. It's a two-step in the bottom group. So we can ask if there is such a thing. There's one way of defining. So now there are several ways of defining, actually even the linking numbers. I didn't cover all of them. So one way of defining the linking number would be by topological pairing. So let's wait and do another definition. So first of all, let's consider like S3 minus C1 minus C2. So let's take them away. So let's define it as an integer. That's it, right? So and look at homology. Now, there is a general, what's called Alexander duality. The homology of the complement of something in the sphere is identified as some other homology of what you throw away. Yes? So let me see if I can define it straight. I can put it straight here. So in fact, this Alexander duality is itself a manifestation of the concept of linking. We have anything compact set in a sphere, and we want to relate hi of k, or maybe and hi of say S3 minus k. Right? So in order to write the straight, we can, for instance, consider something. What's the good easier example? It's a concept of, there's a concept of simply connected domain. In the element, they say domain is simply connected if its complement is connected. Right? Let's discuss it.
But for me, simply connected was by one zero.
Yes, of course. But in the old days, they didn't say it like this.
Okay, now I get it. Yeah. Yes.
So there's something here. Okay?
There's a whole.
So in C, which is inside S2, right? So K is simply connected. If it's complement, let's say S2 minus K is means that H1 of K has something to do with H0 of S2 minus K.
Mm-hmm.
And one can write it properly. That would be H2 reduced, H0 reduced, and either way around. So let's put it like this. Suppose this is connected.
Sorry, what do you mean by reduced here?
Let me explain. So it's connected, right? So the complement is connected. So it's simply connected. Which means H1 equals 0. The complement is connected, but not empty. It doesn't say that H0 equals 0. H0 is one dimension. So, but it matches up to this removing this one dimensional thing. Right? So therefore, if I do Hi of S3 minus K, so would be H. I think it would be H2 minus I, something like this. So let's again set it properly. What would be the situation that the complement is disconnected in S3? What would be a domain in S3 in which a complement is disconnected? It would be something like a sphere which subdivides S3 into two parts.
Yep.
So H2 of K goes to H0 of S3 minus K. So from this, this is more or less the identification. Right? So then H1 of K goes to H1 of S3 minus K. And H0 of K. But it here will be reduced. Would correspond to H2 of S3 minus K. So we just implement this thinking. Right? So it means, so now let's take for K the union of, now take for K the union of two circles. Okay? Now take C1 is disjoint. And we conclude that H1 of K. So K equals Z2 with H1 of S3 minus K. H1, so it's disjoint. Right? Yeah. H0 reduced of the Z of the H2. S3 minus K.
This because it's connected.
Yes.
Yeah, okay.
No, K itself is disconnected. It has two connected components.
Oh, but you reduce.
If you reduce, we always say reduce by 1 point.
Okay.
1 point, yeah. And then it's like this. Okay, so it means that there are generators of H1 sort of due to so then.
Oh, and you're back to what you erased up there, where you had Z2.
Yes. So basically, we have gamma 1 correspond to C1. Or we can say that gamma. So in this identification, gamma 1.
Sorry, what is gamma 1?
Gamma 1, gamma 2, and H1 S3 minus K correspond to C1 and C2. C1 and C2. And the gamma in H2 of C2.
That's the definition of the. Wait.
Right? So this one, the generator. Generator of Z. So it's a generator of Z plus Z. Right? So now look at the multiplication. Right. The class of gamma 1. It's already a class, okay, so gamma 1 is gamma 2. We put some multiple M times gamma. With M is the linking number. It's one of the chronological definitions.
But this depends on the choice of the generator, right?
Well, but you can identify them more or less canonically if you trace proposed isomorphisms. The generator corresponds to the fundamental class.
Okay.
Okay.
But for the other one, for the last one, it's not clear, right?
Oh, it's kind of, yeah. But there's only one generator corresponding to some of them together. There is a canonical element. So M is the linking number. So then you similarly do for three things you can write. There's the concept of massive product, which means that you have three elements here. The homology and pairwise product is 0, then is, so I can call. Massive product.
And this definition is convenient because you have the étale homology where.
Yes. This you can, yes, once you do this, if you have some sort of that, then it's more formal. Yes, you can use étale homology and it's all. So we say that some R D is a differential graded algebra. Differential graded algebra. and you have, for instance, A, B, C. For some degrees, say R1, say R1, are cocycles. Or let's like this. Let's say like this. Let's say, for instance, alpha, beta, gamma is elements of the first topology. And you know that alpha beta equals beta gamma equals 0 in H2. So you can differentiate algebra such as the cochains. Later will be the algebra of cochains. Okay? So suppose it's this, we know then, yeah, we can form or triple product called alpha beta gamma. Again, NH2 0. It's in fact not completely unique, but as follows: we write A is the class of alpha is the class of A, beta is the class of B, gamma is the class of C. So we have dA equals dB equals dC equals 0. So then we write, so what does it mean? What does it mean that alpha beta equals 0? Alpha beta equals 0 means now AB is a cocycle which happens to be a cobound. So A and B may not be coboundaries, but the product may be a coboundary. It's G of X. And beta times gamma equals 0. It's BC is 0 for 1.
And X is in H1. It's a one cocycle.
So yes, in this case, yes, a cochain.
Yeah.
That's again a power.
And so then you can
play associativity, right? So what you do, you will normally have to have A times BC equals AB times. That's associative. But you do something like this. So you write A times Y minus X times C. Okay. Then you write 0 of this. Actually, there will be some plus one. Actually, in this case, there should be plus, I think. Yes. Plus, because of the sign rule. Because so you need to be plus because of the sign rule.
Well, we can check and see.
Yes. Yeah. No, but you're right. So equals dA times Y minus A dy plus dx times C minus X times dC.
And then you have that.
So this is 0.
It's a cocycle, and dy is AB. No, dy is BC.
And dx is AB.
Yeah.
Plus minus ABC plus ABC equals 0.
So the claim is that this is a cocycle, so it's well defined on homology.
Yes. So then we get some element of the homology. So that's called the Massey product, and this can be generalized. Now, suppose the Massey product. So now, if I start playing this game, let me play this game a little bit more.
Because you're saying that you may want to have this as a condition and of the same sort as alpha beta equals 0, and you want to have something quadruple or something like that. Yeah.
Yes. Now let's continue. Suppose I have alpha, beta, gamma, and delta. So actually, if I start doing this, the relation with the algebra or group of upper triangular matrices will become apparent. So you see, I wrote here before, I wrote the group of upper triangular matrices. So resume it. So now, suppose I continue this. So now, suppose we have alpha, beta, gamma, delta. We can be in arbitrary degrees. It's just a question of adjusting the signs, right? H1. Right? Suppose that alpha beta equals 0, beta gamma equals 0, gamma delta equals 0. And suppose product alpha beta gamma equals 0. And beta gamma delta equals 0.
And you don't need the others. I mean,
no, I don't need that. So it works like this, yeah. So in fact, there is I skipped a little because this has some ambiguity. I said that it lies in H2, but it's not fully lies in H2 because we can analyze what happens if we change X and Y. So it's not exactly in H2. It lies in certain quotient of H2.
If you change X and Y by a boundary.
Yes. So suppose X and Y will be X prime. But then d of X minus X prime equals 0. So X minus X prime plus Y is in H1. Okay.
You don't change them by boundary. Okay.
Yes.
Okay.
So then the result would be a multiplication of A with H1. Right?
Which result?
The result of, if I write a new thing.
With X prime.
Yes, with X prime.
Yes.
I write H1 times C. I may get some other element of H1 times C.
Okay.
So
modulo it's modulo H1, you see.
So it's not modulo H1. So formally now I say ABC is when A alpha beta gamma defines in H2 of R. Modular A times H1 plus H1 times B. So alpha times H1 is H1 times gamma. So really, the final thing is the massive product we have in the determinacy. So if it argues commutative, it doesn't matter. The non-commutative is like this. Right? And this is indeterminacy. Now suppose I have this condition, so this is 0 in the homology, and this is 0 modular indeterminacy. It's 0 indeterminacy. So now let me write those indeterminacies. Let me write that suppose this product is 0 and this indeterminacy. Right? Then I have a bunch of elements of my DG algebra. And out of them, I can construct yet another element, which will be closed. To the point that this element is closed. It's a cosac. Right? Out of them, I can construct a new cosac. Basically, if I write everything here, I write that, okay, so I write here, so alpha beta equals 0, I have AB equals dx. Well, I already erased it. I have A.
You had XC and
A, so it would be A, B.
Yeah, you had XC minus or plus or minus, and the other one was
so we
AY.
have dx equals AB, dy equals BC.
Yeah, and you had AY.
So dz equals C times D. Okay. So then I write A times Y plus X times C, right? This represents this thing, right?
Mm-hmm.
And here I write.
But you had a sign, no?
Plus, with the plus sign. So far we with the plus sign. If everything is.
Oh yeah, yes. Okay.
So here I write B times Z plus Y times D. Right? So this represents.
Yes. Okay.
This represents beta gamma delta.
Okay.
Right? So and then I write that this is equal in A. So lies in this class. So equal to A times H1 A times H plus so let me write differential by delta. Oh, that's also delta. Okay, that was A comma H plus D of something. plus d of k.
Sorry, what this leaves? You're saying that this leaves
In the determinant. So what I'm saying that suppose I write all those things that they are in the determinants.
So it means that what you have written here is in H2 modulo what's on the right. So this is equal to the same thing.
Suppose it lies in alpha H1 plus H1 times gamma.
But why do you say it has to be there? It is well defined modulo that thing, right?
Yes, but suppose modulo that thing is zero. I want to say that the next one is always defined.
Okay. Yeah, that's what you wrote. Zero.
Yes.
Okay, sorry.
Suppose it's equal to AH1, AH plus AH prime plus H second gamma plus D plus H C plus D of some element U. And this is equal to D times K prime plus K second times D plus D of some element. Then out of those elements, if you think just a little, I think one should look at U and V, and I should take U times D plus or minus A times V. Here.
Because morally U depends on A, B, C, and V depends on B, C, D.
So here you see the first, because so the D is a cycle, so it's equal to du times D.
Okay.
D of U times D. D, and here it is. So I will do plus here, and that will be I will get minus A times D of V.
Okay, and then we replace there.
So D of U.
Yeah, is A.
So suppose I have minus.
Yes.
With the minus.
So DU is AH prime,
AH prime
plus H double prime C.
C times D.
Yeah.
Minus
A times B times K prime.
Times B K prime. Plus K second. D.
Yeah, there was a parenthesis here.
Then there may be one more correction term which I should insert here. So far what we have.
This.
But this is equal to, so just a moment, but this thing, but this is equal to AY plus XC, right?
But you want to...
So, and this is equal to AY plus XC. So D of U equals, I just lost.
You want to have some new indeterminacy up here, right?
No, so D of U is not equal to this. D of U equals this minus this. Yes, but anyway, so I may be losing myself now, but it would be this minus this minus this times D plus A times this minus BZ. Right? So and then something here will cancel with AY.
I mean, we have AYT over there. Yeah, the AYT cancels, except for sign.
Yes. So and then would be okay. I might not be able to do it right now, but basically you go like this,
yeah,
and you go like this forever.
Okay, you get higher, let's see.
Extracting new kind of extracting new homotopies, and eventually you get this element. So then the previous is 0, and the next one appears.
And you mentioned the Heisenberg group here, because you said.
So what we do is simply let me consider the prime example of my C products. So this is so what I said about the linking number is an applied example. So, but the sort of topological example of my C products. So topological example. So first is a group. This Tn is a group of matrices like this. That's I can do over in a ring. Let's consider Tn of R. What Tn of C? So this manifold. Well, so Tn projects on the group of on the additive group A1, An minus 1. Additive group. So the vector group. So it projects into R n minus 1. What is it n minus 1? So there are classes. So there are canonical. So canonical. Alpha 1, alpha n minus 1, and H1. This one. With real coefficients.
Sorry, I'm not sure.
So so this is torus.
Yeah, yes.
What we'll have will be that alpha 1, alpha 2, alpha 2, alpha 3, alpha n minus 2, n minus 1 equals 0. So the cohomological products, the usual cohomological products.
So I was not sure what are the alpha i's. How do you get them from the?
No, it's a torus. We just lift them.
So you just take the cycles into no. I'm not. I'm sorry. I'm missing something here. What are the alpha i's on M?
Alpha i's are so there are classes here. So alpha I like in H1, Tn minus 1.
Ah, okay, no, okay. Yes, okay.
So then we have the full bracket of the massive product, and then but this is A n minus A1L. So there will be a class. We will be able to go all the way.
So what's the link between the alphas and the A's? I mean, you seem to.
I'm saying consider this Heisenberg quotients. So AI lie in R mod Z. If you consider this.
Okay. Yes. Okay.
There is one version, and a similar version would be if we consider the Heisenberg group mod 2. So we consider Tn.
But sorry, there's something here, because you could have the alpha i's for whatever map which has a map to Tn minus 1, right?
Yes.
But here you have something very special about the form of the Tn's, which enables you to make some statement on there.
or how should I say?
Basically, this statement is that you have all the massive product equals 0. That's probably what you want to say here, right?
Yes.
And this way you can get all the massive product to
So
all others.
Until the very last one.
Yeah.
So
that's
the
the
last
claim.
one to be defined. Yes. You have sort of this. How should I put it better? Oh, okay. So let me get an example. Maybe that's not such a good example. Consider it differential graded algebra in which I will exactly get this thing. Consider, so define R generated by, so with generators Z1, 2, Z2, 3, Z3, 4. First of all, on which differential would go to 0. And then, for instance, would be in degree 1. Right? So I'm defining another generators Z13, Z24, Z35 will be like Z13, Z12, Z23, D of Z24, Z23, Z24, and so on. Then I have generator Z14, Z25, Z36, and so on, such that D of Z14 equals.
It should be Z13, Z34 plus.
It will be Z12.
No, yeah, this is
Z24.
Yeah, and
plus
Z13,
Z13,
Z34. Yeah.
And so on. So the generators of the form is ZIK. So if you do this, so if you want to construct a model algebra, right? Yeah. So a model algebra for massive operations.
But it looks a little bit like the infinity.
Yes. So it looks like familiar things. You can start like an elementary model for massive operations. So algebra is the universal thing. When we define a massive operations, we get a homomorphism from this.
Yes.
In order to have it, we simply have this. Yep. So we have generator Zij, and we have the G of Zij equals sum over K between I and J plus minus Zik to Kj.
And
so each time what I write.
Yeah, and why do you want it to be quadratic? You could have also.
No, but then all the way up to Z1n. So then, in this algebra R or Rn, let's define this differential graded algebra. In this Lie algebra, the class of Z1, 2, class of Z2, 3, class of Zn minus 1n, if the massive product is defined, so it is well defined. So is it because each time that we sort of how should I say?
So you're claiming that what we made before, the construction we made before, should work here too?
Yes. So in the sense, the thing, this class is well defined. So and suppose we don't include. So if we include it, this well defined is 0. If Z1n included, this thing is defined in 0. So this is a sort of universal thing for massive operations. But now it has, so this simply is the cochain complex of the Lie algebra of upper triangular matrices. So consider for G is the Lie algebra. So I don't know. So over any field or over any field, say over C. So it's simply this is.
But then I don't read well the Zij.
So Zij are generators. So they all agree one.
So they are all the dual of G actually. Okay, now I see. So the
the
dual.
Okay, yes. So what is the
yes.
What's the co-chain complex of Lie algebra?
Yep.
We put dual generators in degree plus one.
Yep. Okay.
That's a formula exterior algebra. So at the commutative level, it will be simple, right? So this shows what this thing has to do with upper triangular matrices.
Okay. Yeah, the universal Massey algebra is this homology. Okay.
Yes. So if Massey operations are defined at 0, then we have the map from this thing. So this means that we can also define. So it means that we can define the n-fold linking number by considering Galois cover, the existence, the vanishing of previous Massey products amounts to existence of Galois cover with this group of Z mod 2, now translated into situation of modulo 2. And then the next thing would be the Jack transformation lying in this group, and only one element will be non-trivial.
Sorry, once again.
So now compare this. Compare this with the definition of.
You want to recover the n equals 2 basically, but so the Legendre.
Yes.
So you're saying if you want to have the Legendre, it means you have just one guy.
Yes.
Okay, I see.
Yes. So if I have Z1, 2, Z3. So now let's consider the algebra sort of Heisenberg-Lie algebra. Heisenberg-Lie algebra of C, right? So it would be the algebra generated Z1, 2, Z3, and Z1, 3. So it's a co-chain of this. It would be algebra generated by D of Z1, 2, D of Z2, 3, 0, D of Z1, 3, Z1, 2, and Z2, 3. So which means that if there are two cohomology classes which multiply to 0, then there is a homomorphism from this algebra to the co-chain algebra.
Sorry, once again.
If there are two cohomology classes,
Z1, Z2, 3, yeah.
Then there's homomorphism from the co-chain algebra of this thing.
Okay. Yep.
Yeah. So it's similar situation. Let me maybe skip it a little now. So to compare this. Prepare this better. So if R D is any DG algebra, DG algebra with alpha beta H1, that is alpha beta 0, there exists a homomorphism of C dot.
Yes. Yeah. Okay.
The Lie of Heis.
Yes.
Into R.
Yep.
I want to compare this with the situation if C1, C2 inside S3 are links or knots with C1, C2 equals 0. Yeah? So Galois, so mod 2. In fact, if it's not 2, it will be cover mod Z. So in Z, let me do it. So Galois cover of S3 minus C1 minus C2 with group